Hi, today we're going to get started in a new unit, so it might be a little bit of old information, definitely a bit of new information. To get started, we have some videos here to watch. Obviously, you're going to jot down anything you find that's interesting. I don't have as much room here, but I'll do what I can. So just while it's playing, there isn't much sound. I might as well talk. We have an hour-long time lapse on your left. I don't think that's a full hour on the right. Dry ice versus ice, and we can see some differences here between them. I do see this snow around the side. Specifically, that's not the snow that you're showing up over on this side here is not something that's coming off of the dry ice. It's actually it's condensing water vapor in the air around the dry ice. And just to make my point as for the time lapse, I find it particularly meaningful, like go to the beginning and then go to the end, just to see the difference in how much smaller it gets. And this one's also getting smaller. And you can see over here we've got our dry ice basically disappearing. I don't know where it is. There is this liquid around here, but like I said, we'll talk about that on the next slide. But what is dry ice? And what makes it dry, basically, right? That's the big question. We're going to maybe touch on most of this, maybe not all of it. So like I said, the smoke and the snow that you're seeing around this dry ice is actually condensed water vapor from the air. Really what's happening to the dry ice is, you saw in the video on the right with the watch, it's disappearing, turning into a gas. Dry ice is made of solid carbon dioxide, which is not commonly found under our conditions here, and undergoes a process called sublimation, meaning there will not be, under these conditions, spontaneous formation of liquid carbon dioxide. It can be done under certain conditions, but I'll save that for another time. The other interesting point I wanted to make between dry ice and, I don't know if I want to call it wet ice, solid water, it's definitely missing a degree symbol here. Much better. The bigger difference between them is the temperature at which the transition occurs. Just because they're both sitting in a room doesn't mean they're both at room temperature. They're warming up. What we're seeing here in this image occurs at negative 78.5 degrees Celsius, and then the ice that you're familiar with, the frozen water, melts at 0 degrees Celsius. I guess it would probably be beneficial to put some chemistry, some formulas, some symbols to it to clarify, but there's two big questions I have. One, what is sublimation? How does it happen? Why does it happen? And then the other, why are we seeing this difference in transition temperature, melting point? I guess you can't call it melting if it's not turning into a liquid, but we should definitely talk about that. So here we have our wet ice up here. I do want to talk about phase changes, which, as it says here, talk about this. The substance isn't changing, but its arrangement is. Remember, the solid, liquid, and gas had definitions for their shape and volume. And so what we're seeing here with this melting ice is a solid with a definite shape transitioning into a liquid. The particle arrangement's changing with an indefinite shape. Its volume is still constant. Since these are phase changes, and since there is some change in some things that aren't changing, it might be beneficial to maybe even write a chemical equation to show it. So for this ice melting, maybe it's better to start calling it solid water, and we would show that there is a transition happening to liquid water. Now you can see. We can show the phases as subscript or not subscript, up to you. But it is important to show it. There are 6 changes between the 3 phases that we're talking about in this course. The new ones that you might not recognize are sublimation and deposition. They're opposites of each other, going from solid straight to gas without liquid forming, and going from gas straight to solid. You may have actually seen some small amount of sublimation take place. I don't know if you've ever done this. If you've ever taken a snowball and tried to put it in the freezer until summer, you might notice that over several months, that snowball has shrunk, but it didn't melt. That process, under those conditions, you're getting a tiny amount of sublimation happening. So you may have actually witnessed it before. But to put some more definitions to these phase changes, they happen at what we would call a melting or a boiling point. And that point is a temperature point, the temperature at which you will see the solid to liquid transition spontaneously. There's the spontaneous I wanted to mention. The only difference between melting point and freezing point is whether you're going from solid to liquid or liquid to solid. The temperature at which it happens is the same. That is to say, in Celsius, ice will melt at 0 degrees Celsius, water will freeze at 0 degrees Celsius. The same is true of boiling and condensation. That's the same thing, except it's liquid to gas and gas to liquid. And I guess there is a sublimation point for those special substances that undergo that process, and a deposition point. Same temperature, opposite process, opposite change. So I kind of want to steer us in a bit of a direction here. We've seen these before, earlier in the year. These words, melting point and boiling point, on table S of your reference table. There's two things that show up here that kind of cause me some concern. One, yeah, there are melting points. They're listed for elements, but there's this K here, and that K doesn't mean potassium. So how do we figure out the melting points for compounds? Because we know that after a chemical change, the properties change. And then again, we still haven't really addressed this question of why do we see different numbers for different elements? Why do we see different numbers for carbon dioxide and for water? So why do substances melt in the first place? Before we get too deep into that, I did think it was a good idea. I always have a question when I want to address this in the year. Temperature. I just want to come out and say it. Temperature is a measure of the motion of the particles in your sample. That's all it is. That's its definition. That's it. It's different than heat. We'll talk about that later. A high temperature means your particles are displaying more motion. A low temperature means they're displaying less motion. And there are several scales on which temperature is measured. Yes, Fahrenheit's right there. And now I'm done talking about it because, we're not worrying about that in this course. As scientists, we use Celsius and Kelvin, the SI unit for temperature. Fahrenheit, okay, I'll talk about it for just a minute more. Fahrenheit's useful for weather. Most temperatures, we are humans, we like dealing on a base 10 scale. Most temperatures that you will see in nature, in weather, occur between roughly 0 and roughly 100. Does it go above and below? Absolutely. But it puts those numbers on a scale we process a little nicer. When you use Celsius to talk about weather, the range is from, -10 to +30. And that might not make sense to Americans. It definitely makes sense if you're not in America watching this and you've grown up with the Celsius system. So I'm working on it myself. I've been trying to train myself. I remember 37 is human body temperature, so that gives me a bit of a frame of reference. But you see there are other reference points here, too, between all three of these scales. Of particular note between Celsius and Kelvin, let's not worry about the Fahrenheit. I want to point out these numbers and how they differ. You'll see that the numbers, the difference between the temperatures, the freezing point of water and the boiling point of water, is 100 degrees Celsius. And then for the Kelvin scale, it's also 100 degrees. Now, the word degree doesn't get used when we say Kelvin. They just call it 100 Kelvin, or 100 kelvins, some people. But the difference is the same. So that is to say that the amount of change in temperature, the amount of change in motion that causes a 1 degree shift in Celsius temperature is the same as in Kelvin. So that's kind of useful for us to use. That means to convert between them, there's no multiplication or division, it's just an addition. Celsius plus 273 is Kelvin. Depending on if you have a decimal place, you can use that in your calculation, but you don't need to, but you can see that on the picture. So now that we have this idea of temperature, we can fold in this idea of why phase change happens at all, and that might give us a little bit of information as to why it happens at certain temperatures. What we have here is pictures of molecular motion, particles that are together. We've been saying for years, you've learned for years, that a solid is a solid because the particles are packed tightly together. But they're particles. What's packing them there? What's keeping them there? There's always these two oppositions in particle behavior. Particles are always moving because there is a temperature, and the only time you get no motion is with no temperature. I suppose that is worth saying for the Kelvin scale. You'll notice that the lowest temperature, this absolute 0, is 0 Kelvin. So Kelvin scale is built such that all temperatures are positive. It's called an absolute scale. For Celsius, obviously negative temperatures exist, the same with Fahrenheit, but Kelvin doesn't work that way, and that's why we have two different scales, the Kelvin and the Celsius. because the universe doesn't care at what temperature water melts. But it does care about molecular motion being zero. But there is also this other factor in these particles. It's not that the particles are tightly packed. That the word pack makes it seem like something's pushing them there. It's quite the opposite. Something's pulling them there. We learned about ionic substances and that there was attraction between these particles. In fact, a lot of attraction. And that attraction causes the solid to be a solid. That's what's holding the particles there. Well, then why does a solid ever become a liquid? Well, we know that if we want to melt a solid, you heat it up. You take something out of the freezer and you let it sit. You put something on the stove and you heat it up, and it would melt. If you put plastic on your stove, don't do that. It would melt. So it's this constant argument between the motion of the particles and the attraction they have for each other. In the solid phase, there's more attraction, and in the liquid phase, there's more motion than attraction. That said, that the attraction that we saw in the ionic solid is based on the charges and how they're structured, how the ions are formed. We'll talk a bit about structure for covalent substances later. That attraction doesn't change. That's based on the charges and the structure, and those are fixed if we're talking about physical changes only. So really, it's not more that the attraction decreases, but that the motion increases. And so as a substance is heated up, as its temperature increases, eventually the particle motion gets so large that the attraction holding the particles together is overcome. The same could be said in the opposite case, which is what the image is down here. Someone has boiling water coming out of a tea kettle, throws it in the air, and it almost instantly turns into ice crystals and cloud. It's recondensing, it's cooling down. So as the particles slow down, eventually the motion can become lower than the attraction, and that's what we would call condensation or freezing. So this is all building up to this idea of saying if we're talking about the temperatures at which this happens, then we need to start talking about putting some sort of justification, some sort of evaluation to the attraction and the motion. When we have the evaluation of the motion, it's called temperature. We have some idea of what the melting point is because we can see that certain substances have higher melting points and then certain substances have way lower melting points. These are all in Kelvin, so if you wanted Celsius, subtract 273. So the ionic substances, that's clear. You have a lot of charges, you have a lot of attraction. The metallic bonding, you have that network of electrons floating around. Again, you have those charges. For the covalent substances, there's no charges. Particularly fluorine, chlorine, bromine, and iodine. In a molecule of fluorine, you have your Lewis structure showing that all the electrons are equally shared. If the electrons are equally shared, there's no poles, there's no negative side, there's no positive side, there's no negative particles, there's no positive particles, so there's no attraction, right? Well, no, not right, because not only does fluorine have the ability to exist as a solid, it's actually, you can see a trend in these melting and boiling points. Iodine has a higher melting point than fluorine, and iodine is actually a solid at room temperature because that's above 273 Kelvin or 0 degrees Celsius. That's above 100 degrees Celsius, actually. That's a really high melting point for this kind of thing that has no attraction. So there's something going on there. And that something is called London dispersion forces. Because while it's true that there is no charged side of things in fluorine, I'm wrong to say that there aren't charges. There are charges. There's protons and there's electrons. And so there is this force that holds them together. There has to be that attraction if there is not only a number that's not 0 Kelvin, but also a trend. There's some sort of process has to explain the increase in melting point between fluorine, chlorine, bromine, and iodine. So like I said, there are two charges in every single type of matter. If there are atoms present, there are charges. Those charges are protons and electrons. The protons don't do very much here. They're stuck in the nucleus. But those electrons, don't forget, are electron clouds. And that cloud has the ability to be, it's evenly distributed, sure, in a particle, but evenly distributed does not mean in all places at once. Over time, it's evenly distributed. But if you ever stood still and took a quick picture and paused the animation, you would see that at any one given time, there's a chance for all of the electrons to be on the left side of a particle. It's a chance. It's based on statistics. It's temporary. That's not really good. That's not going to be really strong or long lasting, but it is non-zero. And so this would make this look polar for that brief moment. And in that brief moment, if there is any sort of chance for another particle of the same type to wander by, you can get a rough attraction where the positive side of this temporarily imbalanced particle attracts the electrons in the adjacent particle, pulling its electrons over to the side, causing another partial charge in that second particle. You have a particle-particle interaction, an intermolecular force between your particles. And that causes the weak attractions that we're seeing that cause these fluorine, chlorine, bromine, iodine to turn into liquids and solids at very low temperatures. The same could even be said, this is not a molecule, this is a particle. The same could be said for any particle that apparently doesn't have any interaction with any other particles, like noble gases. Helium particles, neon particles, they have really low melting points and boiling points, but they're not zero. So you see this process over and over again, where as these particles have these charges, they can shift over to one side or the other. And if you want to really exaggerate it, you could say, like, temporarily those shared electron cloud electrons can be, like, way over this side, which would cause this side to have a tiny negative and this side to have a tiny positive, which could then interact with a neighboring fluorine. It is also true that we see this trend. Well, if this attraction is based off of electrons, well, then it would make sense that more electrons could cause more of a lopsidedness, which would cause more of a charge, which would cause a stronger force and therefore a higher boiling point, a melting point. And that's what we see here. These are all sharing one pair of electrons, but don't forget that there are those internal electrons that can shift too. And fluorine is atomic number 9, and chlorine is 17, and bromine is 35, and iodine is 53. And so those internal electrons can too shift around, and that will show you what you see here. It is instead said, instead of having to go look up the atomic number of everything, frequently we would look at the masses. So fluorine has a mass of 19, 19 is 38, chlorine is about 71, bromine is about 160, and iodine is... You gonna make me look it up again? I'll look it up again. That's 254, which is 127 times 2. So there is a clear trend there, not just between the atomic number, but also the mass. And the mass, you would also maybe guess that this would go in the opposite direction. As the molar mass gets lower, you see a lower and lower melting point, and that does show with, as it goes down all the way to helium, one of the lightest particles. I believe it's around 30 or so, 30 Kelvin, where this transition occurs, and hydrogen's also way down there. It might even be like 4 or something. No, I'm confusing that with water and Celsius. So just for a frame of reference, we can see that this trend also fits with carbon dioxide. Remember we said negative 78.5, really freaking cold. To turn that into Celsius, we would take that number, right? Kelvin is Celsius plus 273, and that would be approximately 195 Kelvin, give or take, 194.7. So hopefully this would give you a bit of a frame of reference. The molar mass of carbon dioxide is about 44.01, and so that would mean that this would fit roughly around the chlorine. But you can see it's in the ballpark, and so that's what this is really all about, saying a relative ballpark. So to sum things up, there are these attractive forces that help dictate at what temperatures, at what molecular motions phase transitions occur. The weakest of which we talked about today was the London dispersion force, sometimes just called dispersion force. And it's this attraction based on shifting electrons and luck and chance and probability, but it does happen. And when it happens, you see a stronger force holding together the bigger, heavier, more electron-filled particles. And so this general upward trend on the noble gases we see on the bottom is explained by the dispersion force. There is this idea of you can overcome that attraction by increasing the motion and the temperature, so the phase transition occurs. And I know what you're thinking. You're wondering what these other lines have to do with, why they're higher in temperature than the line I just indicated, and what is going on with water that makes it seem so out there compared to everything else. I think I'll save that for next time. Thanks for watching.